Okay, so hi everyone. Um, so today is obviously election day. So if you are a US citizen and you haven't yet voted, then please do vote. Um, I'm not going to tell you who to vote for, obviously, but yeah, for those of us who live in this country but aren't citizens and so don't get to vote, then you know, appreciate that everyone who can gets their voices heard. Um, okay, so last time we talked about sort of continuous time, evolution of open systems. And what we saw is that if you make this assumption that the evolution is Markovian, so the evolution from time t to any future time is just given by some quantum channel with input just the state of that time t. So information that never leaves, never comes back in. Then what you get is what's called the Lindblad-Master equation. Okay, and we sort of played around with some simple examples of that. So today, last few lectures have sort of been slightly random one-off topics. Today we're going to start a real, next 3 lectures all on one big major theme, which is going to be obviously quantum error correction, which is a huge, major thing. And the reason it's such a major thing is, even if we get way better than we are now at making quantum computers, and can have like millions of qubits and stuff, then those quantum computers aren't going to be perfect. They're going to have flaws, they're going to have errors, and without quantum error correction, it's really quite a magical thing that it's possible at all. Then we'd be in major trouble. Hang on. So let me plug my iPad in. Okay. So in particular, just to give you a quick comparison, back in the 1950s or so, what's called analog computers were like kind of a big thing. Not like digital computers today, but they were a thing that people used. Basically, what analog computers are is they're just storing data and manipulating continuous variables. So rather than just zeros and ones, classical bits, then you store information in, say, like the charge on a capacitor, or like the exact voltage across some thing, or you can even do it like have them work mechanically rather than electronically. There's all sorts of ways you can do it, but basically they're all just about using continuous variables rather than like discrete bits. Okay. And in an idealized world where you make an exact analog computer, then these things are really powerful, right? You can do crazy things because a single continuous variable thing, for example, can formally store infinite amounts of information. But of course, that world doesn't exist. And the moment you add in noise, then they have no advantage for anything over digital computers. They can be efficiently simulated on a digital computer. And in fact, they also don't obviously have a disadvantage, but in fact, obviously, digital computers ended up having much better error scaling, being much more robust, and took over the world. So it was a natural question when people first started thinking about quantum computers with Feynman and then David Deutsch, Peter Shor, and so on. A reasonable critique was, well, this just sounds like analog computers, right? Like the quantum state is like a continuous variable thing. You have these infinitely many states of a qubit, and sure, that naively lets you do more powerful stuff. But like in practice, it's not going to be any better than an ordinary classical digital computer. But it turns out that this is not the true. quantum computers genuinely, even when you include noise, they genuinely are more powerful than classical computers. And the reason is, of course, because we can do quantum error correction, which for a classical continuous variable thing, then if you have a little bit of noise, then that noise is completely uncorrectable. Okay, so let's start with something a bit simpler than quantum error correction. Quantum error correction is a fairly sophisticated subject. We're just going to start with classical error correction. So how does classical error correction work? Well, the idea is we have some bits storing some data, but then there's some noise. And so some of those bits can get flipped. It can start in a 0, but then there's some probability that it gets flipped to being a 1, right? But we're going to assume that the probability of that happening is very small. We're going to assume our classical computers are pretty good, but not completely perfect. And so then we want to be able to use error correction to make our data storage more robust. Anyone have a idea of how we could protect a single classical bit against an error happening?
Make copies of it.
Awesome. So that is indeed the simplest classical error correcting code, just called the repetition code. So what it means is that if we want to store a 0, then the code that we store it as, the way we encode it, is just going to be 3 copies of 0. Similarly, if we want to store 1, we're going to store it 3 copies of 1. Okay, and then we maybe have some noise applied. We leave it for a while. Stuff happens. There's some chance of bits getting flipped, and we want to recover from the noise. And the way we do that is just what's called majority decision. Okay, so what this means is if there's 2 or more 1s when we come to look at it after the noise, so maybe things have changed, then we just assume that the real state that was wanted was all 1s, and we flip the 0 to make it all 1s. Okay, but if on the other hand it was majority 0s, then we assume that it was really all 0s. We flip the 1 to make it all 0s again. Okay. If at most 1 bit has got flipped, then we successfully recover the state, right? But if on the other hand somehow 2 bits have got flipped, we got particularly unlucky, then we're going to conclude that actually it was the 3rd bit that got flipped, and we're going to end up going back to the wrong state. Okay. On the other hand, if the probability of a bit flipping is very, very small, then the probability of 2 bits, if that's the probability of any of the individual bits flipping is very small, then the probability of greater than or equal to 2 out of 3 flipping is order p². Okay, so by using this repetition code to store the data, we've dramatically decreased the chance of an error happening. Okay, an unrecoverable error happening. Okay, any questions about classical error correction? At this level, it's pretty simple. You can get fancier and talk about fault tolerant classical computation and stuff. Another interesting point is that this whole theory of classical error correction and fault tolerance and so on, it gets a much richer theory than just this when you start to talk about like doing computations on your classical objects. It was all developed back in the 50s and 60s. And then, it's this very rich theory. And then classical computers got so good that like for ordinary computers these days, they just don't use any fault tolerance at all. They just assume that there's no error. Like maybe your data for long-term storage, you back it up a bit in case your hard drive gets corrupted. But for the actual computation that's going on, they're not using any fault tolerance at all. Quantum computers will definitely never be like that. I think I can say that in pretty high confidence, at least for like 1,000 years or something. Yeah, any questions about classical error correction? Otherwise, I'll go on to what happens quantumly. Cool. Okay. So what about quantum error correction? Well, the big difference with quantum error correction is whereas before the only thing that could happen was a bit get flipped, now we sort of have infinitely many different possible errors, right? So, we could have like some like arbitrary unitary getting applied to the state, right? There's infinitely many unitaries. You could have the state getting measured, right? Or become entangled with the environment, like basically the same thing, decohere with the environment. There's infinitely different bases that can happen in. So there's some huge range of things that in principle we'd want to be able to correct. And so that just seems totally impossible. And magically by the end of this lecture, we're going to be able to do it. But instead, we're going to assume, just for the moment, that the only possible errors, put errors in quotation marks the only possible errors are bit flip errors, just like the classical the classical error correction problem, right? An X gate gets applied to a single qubit. But of course, as with the classical thing, we don't know, this X gate is an error. It's not something that we deliberately applied to. We don't know which qubits got flipped and which didn't. Okay, anyone have an idea about how we could try and protect against these bit flip errors? Think about what worked for the classical case.
You could try the repetition code again.
Indeed. Okay, so let's try that. So what we're going to do is we'll encode we're going to encode 1 qubit into 3 qubits. Okay, so the 1 qubit is the logical qubit. It's the actual information that we want to store. The 3 qubits are the physical qubits, and so this is the logical qubit. This is the information we're actually trying to store, and then we're going to encode it as 3 physical qubits. I'm just going to encode the 0 state as 0, 0, 0. Okay. And the 1 state for the logical qubit is going to get encoded as 1, 1, 1. Okay, so the tildes represent that it's the logical qubit as opposed to the physical qubits. Okay, but we should think of these two, the two sides as being the same state. Okay, and so just by linearity, that must mean that we encode some superposition of 0 and 1 as alpha times 3 zeros plus beta times 3 ones. Okay. So then we have some noise where one of the 3 qubits can have an X gate applied to it, or none of them can. And we're going to try and recover the state. We're going to just recover it using the same sort of majority rules that we use for the classical thing. Okay, so how do we do that? Well, we're going to do it using the following circuit. So we have our 3 qubits. We're going to get 2 extra qubits just in the 0 state. Okay, and then this top ancilla qubit, going to apply a C0 based on the top qubit, and then a C0 based on the middle qubit. And then for the bottom ancilla thing, we're going to apply a C0 controlled by the middle qubit, and a C0 controlled by the bottom qubit. And then we're just going to measure both of our ancilla qubits. I claim those measurements are going to let us determine the majority rules, basically. So let's see how this works. So let's assume we start in the state x0, x1, x2, where x0, x1, and x2 are all just either 0 or 1. Okay, and the 2 ancillas just start in the 0 state. And then we're going to evolve with this little circuit. So because we're working in the computational basis for the first 3 qubits, and they're just acting as control qubits, they're not going to change. They're still going to be x0, x1, and x2. But now the ancilla qubits, so we got started in 0, we got a C0 applied if, we got a NOT gate applied if x0 was 1, and a NOT gate applied if x1 was 1. So this first ancilla qubit is going to be x0 plus x1 mod 2. And the second qubit is going to be x1 plus x2 mod 2. Okay. So measuring the ancillas, lets us determine x0 plus x1 and x1 plus x2. We can think about this directly just on the original 3 qubits as the following measurement. It's just a measurement with measurement operators Z1 times Z2, right? So Z1 is like e to the I, sorry, Z0, let me change my, okay. Let me change from x0, x1, x2 to x1, x2, x3, because my notes have managed to switch over between the two later on. One, two, three. This is sum of x1, x2. This is sum of x2 and x3. Okay, so this is equivalent to doing a measurement where the measurement operators are z1 times z2. Okay, so z1 is e to the I x1. Z2 is e to the I x2. So z1 times z2 is e to the I x1 plus x2, right? So we'd have a measurement outcome of -1 if x1 plus x2 is equal to 1, and 1 if x1 plus x2 mod 2 is equal to 0. Okay. And the other measurement, the x2 plus x3 measurement, corresponds to a measurement operator z2 times z3 e to the I x2 plus x3. Okay. So, okay, let's see what actually happens if we put in some state. So suppose no error happened at all. Okay, we got lucky, none of the qubits had an X gate applied. Then our state will be just psi tilde, which is just going to be superposition of 0, 0, 0, and 1, 1, 1. Okay, so what's going to happen when we do the measurement? Well, 0, 0, 0 is going to go to all zeros. And similarly, 1, 1, 1, x1 plus x2 is going to be 0, x2 plus x3 is going to be 0. So it's also going to go to all zeros. So the state is just going to go to the original state, 1, 1, 1, tensor 0, 0. Okay, so we're going to always measure 0 for both the ancillas. Okay, and once we measure 0, because it's a deterministic measurement, because we always get the same measurement outcome, then there's no change to the state after measurement. And we have our original state psi tilde, okay? Which, maybe not very surprising because nothing had happened to it in the first place. Okay, now let's suppose an X gate got applied to the first qubit. Okay, so then the state is X acting on the first qubit, psi tilde, which is going to be alpha 1, 0, 0 plus beta 0, 1, 1. Okay, and when we apply the C naught, then x1, in either case, x1 plus x2 is going to be equal to 1 because they're always different from one another. x2 plus x3 are always the same, so that's going to be equal to 0. So this is going to go to just the ordinary state, x1 psi tilde, with the extra qubits in 1 and 0. Okay, so we measure 1 for the first ancilla, 0 for the second ancilla. Okay. Again, because the measurement has a definite outcome, then doing the measurement is not going to change the state. It's going to stay exactly the same. But now let's suppose that when we get that measurement outcome, but when we measure 1 for the first ancilla and 0 for the second ancilla, our rule is that we then apply x1 to the state. Okay, we say if we get these measurement outcomes, if that's what we measure, if we got 0 for both, we just don't do anything. But if we get 1 for the first, 0 for the second, we apply x1. Then the state is going to go to x1 squared psi tilde, which is, of course, just the original state psi tilde. Okay, so if conditioned on the measurement outcomes we get with an X gate applied to the first qubit, we always apply another X gate to the first qubit, then we'll recover the original state. What about if the error was a X gate applied to the second qubit? Well, then the state is going to be superposition of 0, 1, 0, 1, 0, 1, we're going to measure 1 for the first qubit, because the first two are different. First ancilla, because the first two qubits are different from one another. And 1 for the second ancilla, because the last two qubits are also different from each other. And then we can correct the state by applying another x2. Okay, so if we get 1 for in each of the ancillas, then we know the rule is that we have to apply an x2 in order to correct the state, x to the second qubit. Finally, x3 should be obvious how this is going to work at this point. But in this case, it's a superposition of 0, 0, 1 and 1, 1, 0. And we're going to measure 0 for the first ancilla and 1 for the second ancilla. And then we correct the state by applying x3. Okay. So in each case, for each of the 4 possibilities that no error happened, that a bit flip happened on the first qubit, bit flip happened on the second qubit, bit flip happened on the third qubit, we get different measurement outcomes when we measure our ancilla qubits. The state never gets affected, and then in any of the cases, and then in each case, we can correct the state, get back to the original state without any noise applied by applying an appropriate X operator, or nothing at all if no error happened. Okay. So we can summarize this in a nice little table. So we have 3 things. We have the error. We have what's called the syndrome measurement. This is just the measurement of the ancilla qubits in order to detect which error happened. So this is the error detection step. And then finally, we have the error correction step. Okay, so if the error is no error at all, just the identity has happened to the state, nothing has changed, then when we do this syndrome measurement, right, we get x1 plus x2 equals 0. Equivalently, that z1, z2 is equal to 1. Z2, Z3 is also equal to 1. And to correct the error, we just apply the identity. Okay. If the first qubit got flipped, then when we do this measurement, then the ancilla qubit that measures Z1, Z2, going to give -1, right? Like little x1 plus little x2 is going to be equal to 1. So Z1, Z2 is equal to -1. Z2, Z3 still going to be equal to 1. And then we error correct for applying an X gate to the first qubit. Okay. X gate second qubit, we have Z1, Z2 equals -1. Z2, Z3 also equal -1. And we correct with an X2. Finally, X gate on the third. Z1, Z2 equals 1. Z2, Z3 equals -1. And we correct with an X on the third qubit. Okay. Any questions about how that all works? Error correcting bit flips on a quantum computer. Okay. Guess we'll go on then. Okay. The trouble, of course, is the bit flips aren't the only thing that happens, right, in a quantum computer. So what's another sort of error? Well, if you don't have a Z gate getting applied, you don't have a bit getting applied, a bit flip getting applied. A natural obvious thing, so you instead have a phase flip error, right? You have the Z gate getting applied to a qubit. So let's look at what happens to that with our current code. Okay, so let's say you have a Z gate on that acts on the first qubit, and we apply it to our state psi tilde. Okay, so this is Z1 alpha 0, 0, 0 plus beta 1, 1, 1. Well, that's going to be equal to alpha 0, 0, 0 minus beta 1, 1, 1. Is this an error that we can correct? Anyone want to say anything about that?
I would think so, because we can probably detect the fact that there's a relative phase.
We can detect the fact that there's a relative phase, but we've got to remember that we don't know what the state is, right? Like if we knew what the state is, we wouldn't need to be error correcting it. Okay, so all we know is we could like do some measurement that like determines that the state is now alpha 0, 0, 0 minus beta 1, 1, 1. If that's the state, does that mean that an error has happened? No, right? Because this is a sort of possible state even with no errors happening, right? So say if sort of alpha is 1 over square root 2, beta is 1 over square root 2, then e.g., if we start in the plus tilde state, right? The plus tilde state is 1 over square root 2, 0, 0, 0, plus 1 over square root 2, 1, 1, 1. Okay, and then there's a Z error acting on the first qubit. Then the state you end up with is the minus tilde state, right? It's 1 over square root 2, 0, 0, 0, minus 1 over square root 2, 1, 1, 1. Right, that's the way we've encoded, if our actual qubit, the logical qubit that we wanted to protect was in the minus state, it would just be in this state already, even if no error was applied. Okay, it's like if all 3 bits got flipped in our classical repetition code. And like, obviously we're not going to know it was originally 1, 1, 1 because it could have been 0, 0, 0 with no errors happening at all. Okay, so we can't distinguish a phase flip error from just a different initial state. Different logical state, I'll call it. And of course, that means that we can't do error correction. Okay. So that's not good, but we shall not be deterred. We just need to use a different code. What code should we use? Well, Z gates are just X gates, but thought of in the plus minus basis rather than the 0, 1 basis, right? So they're just bit flips from plus to minus and vice versa. And we know how to protect against bit flips. So let's just encode the 0 state as plus, 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 and the 1 state as minus, minus, minus. And then we're going to be protected from Z gates acting on one of these 3 qubits in exactly the same way that we were protected from bit flips before. Okay, because Z acts on plus minus exactly like X acts on 0, 1, right? Like the difference between them is really just a choice of basis for our qubit, the choice of the 0, 1 basis. We call things different names, they'd be exactly the same. Okay. So let's just write out the sort of table we had before explicitly. But really it is just exactly the same code we used before, just in a different basis. Okay, so the possible errors that we just have the identity. Okay, so then what measurement we're going to do? Well, before our measurement operator was like Z1, Z2, and Z2, Z3. So now it's going to be X1, X2 equal to 1, X2, X3 equal to 1. Error correction will just be the identity. We don't need to do anything. Now the possibility is Z1. Okay, how do we detect that a Z1 has happened? Well, we'd have X1 in the plus minus basis, X acts like Z and Z acts like X. So we now have X1, X2 equal to minus 1, X2, X3 equal to 1, just like before, but with Z and X switched. And then we correct with Z1. Similarly, Z2 and Z3 all works exactly the same as correcting bit flip errors, except we changed the names of X and Z to be the other way around. Okay. Of course, no such thing as a free lunch. The problem is that our new code is no longer protected against bit flip errors, right? Because bit flips for this new code are exactly the same thing as phase flips for the old code. And so we're not protected against them. So like X1 acting on plus, minus, 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 right? X1 takes plus to plus and minus to minus, minus. So this is equal to plus, minus, 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 which is, of course, also a logical state. So again, we can't correct the error because our error took one logical state to a different logical state rather than to something new that we can recover from. Okay. So really, the challenge is to be able to correct both bit flip and phase flip errors in the same code, right? Otherwise, you're just moving around the errors that will cause you problems. Anyone have an idea how to do this? It's like non-trivial, but it also turns out to be sort of the stupidest thing you could think of.
Could you just prepare two things to represent both of these?
Yeah, exactly. So all we do is we're just going to put one code inside the other code. Okay, so what does that mean? So in the phase flip code, we encode 0 as plus, and we encode 1 as minus, minus, minus. But now we're going to have each of those pluses, we're going to be encode in turn. Okay? So I'm going to call these double tildes, like the real logical state. The real one logical qubit that we actually want to protect gets encoded as 3 qubits, but those qubits themselves are still going to be logical qubits because they're going to be encoded using the bit flip code. So this is the phase flip. code. And this is going to be the bit flip code. So what does plus get encoded as in the bit flip code? Well, it gets encoded as 000 plus 111. Right. And so our final encoding of our logical 0 state is just going to be 3 copies of 000 plus 111. Our final encoding of the 1 state is going to be 3 copies of 000 minus 111. Okay. So this is the very famous 9-qubit Shor code, or just a Shor code. Invented, of course, by Peter Shor, smart chap. And he was really the first person to recognize the importance of quantum error correction, to realize, holy shit, I have this amazing algorithm for factorizing primes. It's a game-changing thing, but if errors aren't correctable, then it's completely pointless and it will never work. And so he sat down and thought hard and came up with this way to do error correction. Okay, so let's see how it works. So how do we do error correction? Shor code. The first step is that we're going to correct bit flip errors, okay, that might have happened on one of the qubits, okay. And the way we do that is we just correct the bit flip errors in each set of 3 qubits. Right, so we first look for a bit flip error in the first 3 qubits. Okay, they're encoded with the bit flip code, so we know how to do that. Right, so we do a measurement with measurement operator Z1, Z2, Z2, Z3, and then we apply an X to 1, 2, or 3 based on whether we need to, and then we do Z4, Z5, and Z5, Z6. Right, to correct any bit flip errors in the second set of 3 qubits that are again encoded using the same bit flip protection code. And then finally, Z7, Z8, Z8, Z9. Oops. Okay. And apply X gates as necessary based on the rules for the measurement outcomes for the bit flip code. Okay. So now we just need to worry about phase flip errors. Okay. And the important thing is in the bit flip code, right? So on any set of 3 qubits, then Z1 on some state, psi tilde, right? So Z1, so psi tilde is just a superposition of 0, 0, 0 and 1, 1, 1, just equal to alpha 0, 0, 0 minus beta 1, 1. Okay, so what is that? That's just equal to alpha 0 tilde minus beta 1 tilde. It's just a Z operator, we'll call Z tilde, acting on the logical state psi tilde. Right, so a physical Z operator acting on the first qubit does the same thing as first applying a Z operator to the logical qubit before you do the encoding. Same for Z2, and Z3, right? So actually, I'll just so this is also equal to Z2 and equal to Z3, acting on side tilde. Okay. But these logical qubits psi tilde with one qubit, one tilde, are encoded using, they're the physical qubits of the phase flip code, right? And the phase flip code corrects Z tilde errors. Okay, so if Z1 happen, or Z2 happen, or Z3 happen, from the point of view of the phase flip code, where that's just all of those things are just a single logical qubit, all that's happened is that we've had a Z operator get applied, a logical Z operator get applied to that logical qubit, which is one of the 3 physical qubits of the phase flip code. Okay, so how we correct it? Well, we just measure x1 tilde, x2 tilde, and x2 tilde, x3 tilde. Okay, and then apply Z1 tilde, Z2 tilde, or Z3 tilde as necessary. Okay, that's just how the phase flip code works to protect errors. Of course, each of these tilde things are really a logical operator acting on the bit flip code. Okay, so we got to think about what they do to physical qubits, right? So one of the x tildes really takes takes 0 tilde to 1 tilde, but that means it takes 0, 0, 0 to 1, 1, 1, and it takes 1, 1, 1 to 0, 0, 0. Okay, so we can physically implement x tilde by using the physical operator that corresponds to x tilde is just x1, x2, x3. Okay, so really we measure not x tilde, 1 tilde, x2 tilde, because those are logical measurement operators. Really, we measure x1, x2, x3, x4. This is x1 tilde, x4, x5, x6. That's x2 tilde. And we measure x4, x5, x6, x7, x8, x9. Okay, so these 2 measurement operators, they're just the product of all these things. That just corresponds to doing a load of C naughts conditioned on 6 different things, one by one, to store the product of all those x's in an ancilla, and then just measure the ancilla. Okay, and then when we apply, we correct the error by applying Z tilde 1 or Z tilde 2, Z tilde 3, right? How do we physically apply a Z tilde? Well, we already worked that out, right? We know we can do that by applying a Z1 to the first physical qubit. We can apply Z to the second physical qubit, or we can apply Z to the third physical qubit. It doesn't matter. They all do the same thing for the actual logical states. So we apply Z1, Z2, or Z3. If we want to apply Z tilde 1, Z4, Z5, or Z6, Z tilde 2, Z7, Z8, or Z9, Z tilde 3. Okay. So that's the whole error correction process. We just first correct the exit gates in each block of 3 that was in each block of 3 that forms a single bit flip protected logical qubit. And then we correct phase flip errors on the set of 3 bit flip protected logical qubits. Okay. Any questions about that? This is this is the most subtle part of today's lecture probably. So please ask questions if you have them. But it's also something that probably you need to take some time just like thinking about and processing and so on.
So if we're running like a quantum computer with like gates in between, do we have to apply this error correction after every single gate?
Yeah, good question. In a couple of lectures time, we'll get to what's called fault tolerant quantum computing, which is like dealing with the real question of, you're actually doing some quantum computation and it's noisy and you need to be doing sort of error correction as you go and so on. Okay, for the moment, we're just assuming that we're not trying to do any computation. We're just trying to store data and we're trying to protect that data from being corrupted. Make sense? And yeah, we're assuming, for example, that our error correction processes themselves, like these gates they're applying, are still perfect, right? In reality, that's when you're doing the correction, that's introducing more noise from like potentially the correction like isn't really doing what you want it to do and stuff.
Okay.
But at the moment, we're just assuming, we have complete control, but then we leave the state for like a year, and during that year, something like totally fluky might happen. And then we come back a year later and we want to correct things. Make sense?
Yeah. Is there a reason we only use like 3? Like we could use like 5 or 7?
Yeah, so 3 is enough to protect against 1 qubit having an error, right? You might say we want to protect against more than 1 qubit having an error. And then, yeah, you could certainly encode more. What you'll actually find is that these are not the most efficient codes that can be used. Okay, we're going to see like better codes than, even like Shor's code is like, it's the sort of easiest one to understand. It has a nice structure, but we'll see that there are better ones. You can actually encode 1 qubit, logical qubit, in just 5 physical qubits and be protected against single qubit errors.
Okay.
Yeah. Any questions? More questions?
Just one more. When you were talking about like how we can't fix phase flip errors with like the 0-1 bases,
Yep.
Are you like assuming that we don't know what our prior state is?
Yeah, because that's the whole point, right? We're storing some quantum state. If we knew it, we wouldn't need to store it. We could just make it again from scratch whenever we want.
Okay. Yeah. Right. Thank you.
Makes sense? Cool.
So I had a quick question. A little while ago, you said that we could apply we're basically doing a Z1, Z2 measurement. That's e to the I x1 plus x2.
Yep.
Is there like an implicit pi or something like this that?
Oh, sorry, there should have been a pi there. Yeah. Where did I say that? Yeah. That's just me like writing stuff badly.
Okay.
Yeah. Sorry. Thanks for pointing that out. Always good to not have some really stupid things there. Yeah. -1 if x1 plus x2 is equal to 1 mod 2, 0 if it's equal to 0 mod 2. Yeah.
Thanks.
Any other questions? Okay. So this is great. Yeah, we're making a lot of progress. We can now correct sort of 2 possible sources of error at once. But we still seem a long way away, right? So there's infinitely many possible sources of error that are really out there. So this is an improvement, but it still seems like it's a long way from being able to correct all infinitely many possible sources of error. Okay. Turns out, actually, we're done. Actually, this can correct arbitrary errors on a single qubit, which is like pretty crazy and really quite miraculous, and is the thing that makes quantum error correction work. It's just by correcting this finite set of bit flip and phase flip errors, we end up eventually being able we end up being able to correct completely arbitrary errors, even though there's infinitely many types. Okay, so let's see how that works. Okay, so first let's consider a third Pauli matrix, like Y errors. Okay, well, Y is equal to I times X times Z. Okay, so let's look at what that does. Okay, so we have that applied to, so we have a Y, let's say Y1 gets applied to our state psi double tilde, a logical state encoded in using the Shor code. Then that's I X1 Z1 psi double tilde. But Z1, okay, the I we can just ignore, we don't care about it. I'm not even sure it's right. Possibly there's a plus or minus there, but I think it's plus I. So let's ignore the I because we don't care about just a global phase. Okay, so what does the Z1 do? Well, we know that a Z1 acts as a logical Z on our first bit flip code, right? So this is Z1 tilde acting on psi double tilde, followed by an X1. Okay, and we just ignored the I because global phases don't do anything to the state. So, okay, so now we do our error correction. So this is just a allowed logical state of the 3 bit flip protected qubits. So that means this X1 that then gets applied to it gets corrected by the bit flip correction, right? Because it's just the state is just some logical state of the 3 bit flip protected qubits, and then it's had a bit flip applied to one of them, so that bit flip gets corrected. So this then leads to the state just Z1 tilde, psi double tilde. But that is, of course, just a phase flip error. That also gets corrected. Okay, so a process actually corrects Y errors as well, just by like treating them as both a bit flip error and a phase flip error, which is basically what they are. So this shouldn't be surprising to you at all that we also get Y error. This is for free. What should be surprising, at least unless you're more intelligent than me, when I first heard this, is that the infinitely many other sources of error also get corrected. So how do we describe sort of an arbitrary error on one qubit? Well, you just describe it by a arbitrary quantum channel, right? So that can include, some arbitrary unitary getting applied to the qubit, but it also allows us to talk about decoherence with the environment. That's another source of error, right? A quantum channel can talk about like measurements. It can talk about anything we want. Okay, so it's a very, very general thing. So our channel that acts on some qubit I, well, qubit, or just assume it acts on the first qubit for simplicity, because it doesn't matter, they're all treated the same. Okay, it just acts as sum over I, ki rho, ki dagger, for some Krauss operators, rho I. Okay, so a logical state. Psi double tilde, this density matrix is just a cat in a bra. Okay, is going to become just psi double tilde, ki psi double tilde, ki dagger, where remember that the ki's only act on the first qubit. Okay. We can treat this as an ensemble where the state is ki psi double tilde with probability trace of ki psi double tilde ki dagger. Okay, so we're just going to use this ensemble interpretation and say that with some probability, we now have the state ki psi double tilde. It's just a fact about matrices that we can always expand any matrix ki as alpha times the identity plus beta times x plus gamma times y plus delta times z. Okay? So ki psi double tilde is alpha times psi double tilde plus beta times x1 psi double tilde plus gamma times y1 psi double tilde plus delta z1 psi double tilde. Tildes have got a bit straight there. It's a superposition of the different possible Pauli errors. Right, so even though this completely arbitrary error happening to the state, some operator ki, then we can just expand that as a superposition of either no error happened, or an X error happened, or Y error happened, or Z error happened. But now we do the syndrome measurement that is meant to measure whether no error happened, an X error happened, a Y error happened, or Z error happened. And that collapses this superposition, right? It's going to project the state ki psi into one of the four terms in the superposition. Okay, because each of the 4 terms in the superposition gives a different measurement outcome. So post-measurement, state is either psi double tilde, x1 psi double tilde, y1 psi double tilde, or z1 psi double tilde. And then we just do the error correction to recover the original state. Okay, so completely arbitrary things happening to one qubit can be recovered from, can be like corrected, just by being able to correct this set of 4 possible things that can have happened to that qubit. Like nothing happened, X flip, X gate, Y gate, or Z gate. Okay, this is really an amazing thing, and it just follows from like the fact that the way measurements work in quantum mechanics, projecting you into the states in some basis, and yeah, the fact that we can distinguish all these 4 options using our error correction process, measure which of the 4 options happen. Okay, any questions about that?
I had a quick question.
Yep.
So I guess the reason why we don't care what state the measurement takes us to is the fact that we're not trying to do any dynamics. So we don't actually care about the result of the quantum channel, right? We're just trying to recover the original state that we started with, regardless of the channel.
Yeah, exactly. Yeah. Yeah. So yeah, this channel is not some like dynamics that we're trying to implement. This is just like unavoidable dynamics that are happening even though we don't want anything to happen at all. Right? It's a failure. And so we really want to assume that this channel is dominated by the identity with some small probability of something other than the identity happening. Right? And that we just have sort of a small amount of random noise for each of the 9 qubits. But when probably only one of them got affected by that noise, because probably most of them just had the identity. Does that make sense?
Yeah.
If too much noise happened to many, then we're not going to be able to correct it.
And how do you know that the KIs only act on the first qubit? Because I would think that you would have to.
Oh, I'm saying let's assume that an arbitrary error has only happened to the first qubit, or it could have only happened to the second qubit, third qubit, so on. Okay.
Oh, I see. We're assuming.
So a more sophisticated model would be assume that you have uncorrelated errors happening to each qubit, and each of those uncorrelated errors is like uncorrelated channels. It's a product of channels in each of the qubits, and each of those channels is like mainly the identity. Okay, and then where you want to argue that the probability of anything other than the identity happening in each case is small, then the probability of more than one qubit getting affected is like order p squared, right? Just like for the classical thing. Okay, but we're literally just going to assume for simplicity that we don't know which one qubit has got affected, but we know that only one qubit had any noise happen to it. Make sense?
Yeah, it makes sense. Thanks.
Okay, awesome, guys. Okay, so final 10, 15 minutes. I want to back away from the very specific example of the Shor code and just talk about like general rules for quantum error correction. Okay, and sort of the general framework of quantum error correction. So how does this work? Well, in general, we have some set of possible errors. Normally called curly E. Okay, it's just a set of like E1, E2, so on, where these E's are all just operators. Okay, they're different like errors that can have happened to the state that we want to be able to protect. And I think for the purpose of this lecture, going to do what people often do and assume that they're different unitaries that could apply to the qubits. Actually, as we just saw with a quantum channel, what you really want to be correcting is like the different Krauss operators. So if you're allowing decoherence with the environment or stuff, then it can be more general. And it doesn't like change the statements we're going to have really. Okay, so these might be, for example, 1 qubit Pauli matrices. Might be product of Paulis on any 2 qubits. Can be all sorts of things. Yeah, so this is just some arbitrary set of things we want to be able to correct. And of course, as we just saw, it's going to end up letting us correct superpositions of those things as well, right? If our error is really a sum over different e's in this set, then by doing a measurement, yeah, we'll be able to project into one of the things in the set. Okay, so then we need something else to define our quantum error correcting code, which is we need what's called a code subspace. Okay, so that's going to be the subspace of the physical qubit Hilbert space that contains the allowed possible states. So for the Shor code, it's the 2-dimensional subspace spanned by 0 double tilde and 1 double tilde. Okay, and in general, we can assume that it has some orthonormal basis that we'll call I tilde. Okay. Okay, so what we want is to just have a general set of conditions for when quantum error correction is possible. Okay, so let's think about what we need. The most obvious thing is that clearly to do quantum error correction, we need to have that if I start in some state I tilde, then I have some error ek happening to that. If I start in some different state j tilde and have some error el happen to that may or may not be the same as ek, then if I and j are different, then these 2 states need to be orthogonal, right? Because if they started with orthogonal, we need to be able to distinguish the state I with some error happening to it from the state j with some error happening to it. By the way, this set of errors, if you want to be able to protect what we recover if like nothing happens, then you should include the identity in your set of errors. Okay, so we want an error happening to state I to be orthogonal to not just any error happening to state j, but also state j itself, just j with the identity error happening. Otherwise, you can't distinguish no error with state j from state I. Okay. So if we didn't have this, we couldn't distinguish I tilde with error ek from j tilde with error el. Okay. Turns out this condition is not sufficient, That's a necessary condition for error correction, but not a sufficient condition for error correction. And the reason is as follows. Like classically, this would basically be a sufficient condition. You had some classical set of states, you can have errors that can happen to it, and you need your state I with error K to always be different from state J with error L. Okay, but quantum mechanically, suppose we have error 1 happening on the 0 state gives the same state as error 2 happening on the 0 state. So this happens, for example, in the Shor code, right? Z acting on the first qubit has the same effect on the state as a Z acting on the second qubit. But now we're also going to assume that E1 acting on the 1 tilde state is not going to be equal to E2 acting on the 1 tilde state. Okay, again, just assumption. Follows that we can't recover the original state without knowing whether E1 or E2 got applied. But also, we can't distinguish the state after E1 is applied from state after E2 is applied without affecting the state. Right, because if without affecting state, because if psi tilde contains let me say this a slightly different way, because if psi tilde is equal to 0 tilde, then E1 and E2 are indistinguishable. So it's not enough to have I and J end up in orthogonal states no matter what error gets applied, because if two errors do the same thing to I but do completely different things to J, then if our state is a superposition of I and J, we're not going to be able to recover that superposition. Okay, that's just a sort of intuitive argument. You can be more precise about it, and we will be more precise about it next lecture. Okay, so let's try a stronger condition. Natural thing to ask for, so we don't have to worry about any of this, is just that not only is this 0 if I is not equal to J, but it's also equal to 0 if K is not equal to L, right? So each error does something, just puts the state in a completely orthogonal thing. Then we don't have to worry about any of these issues. Then all the different errors are completely distinguishable. So we can determine EK and then recover the state. right? We recover the state just by applying EK dagger, right? If we assume that EK is unitary. So these are called, if it turns out this is a sufficient condition, but it's actually too strong, sufficient condition for error correction, but it's not necessary. But it is true for an important class of error correcting codes, which are called non-degenerate codes. Okay. These non-degenerate codes have a very simple, simple way to do error correction, which is just you do a measurement that lets you determine K, and then you recover the state just using EK dagger. Okay. Of course, as I say, it's not necessary, and in particular, Shor's code is an example of a code that is not non-degenerate. It is in fact degenerate, but whatever, all right, not non-degenerate. So for example, Z1 acting on psi double tilde does exactly the same thing as Z2 acting on psi double tilde. So we can't distinguish a Z1 error, a phase flip on the first qubit, from a Z2 error. But it doesn't matter, and it doesn't matter because Z1 and Z2 always do the same thing to the state. It's not just that they sometimes do the same thing to the state and sometimes do different things. They always do the same thing. And so we can error correct both in exactly the same way, right? You can use the same operator, Z1 or Z2 either works, or Z3 even, will recover the original state. Okay, so errors are allowed to do the same thing. Different errors are allowed to do the same thing to states as long as they do the same thing to every state in the code subspace, every different logical state. So we actually get that the general condition for QEC actually, this one is actually both necessary and sufficient. Is that this inner product between error K acting on state J and error L acting on state I has to indeed be proportional to delta Ij, but it can be delta Ij times MKL for any matrix MKL that just has to be independent of I and J. So the overlap between the different errors needs to be independent. Different errors with the same starting state needs to be the same for every state in the code subspace. Okay, so for example, for the Shor code, if EK is Z2 and EL is Z1, then MKL is equal to 1. Okay, rather than even though K and L are not equal to one another. Okay. So yeah, that's all I have to say for today. Next time, we're going to sort of understand a bit more about why this condition is true. And then we're going to talk about some slightly more sophisticated examples of quantum error correcting code than just the Shor code. So more efficient ones that are more likely to be used in practice. some sort of general frameworks called stabilizer codes for constructing error correcting codes. Any questions?
I had a question about I guess like a technical definition. So
Yep.
like if we're talking about like a quantum circuit, it's like you have some channel that encodes, like whatever you're trying to code in, and then it's composed with like a decoding one that like brings you back to what you should have started with.
Yeah. So the right, you're talking about how we do the encoding, you mean?
Yeah.
The right way to think about it is that the state is always encoded, so you don't need to do an encoding. So you could sort of think of it as a unitary map where you start with just some physical qubits encoding your logical qubits and the rest in the 0 state, and then you do some like unitary circuit that encodes them using this code. But really, like anytime you're going to be storing a qubit, it's always going to be error corrected. And so it's always already encoded, and it's just you're manipulating the encoded states. So you're never actually like decoding or encoding. Does that make sense?
Yeah, I think so.
Cool. Any other questions? Okay. Guess we shall leave it there.